So I want to finish up the components of electric motor. We talked about relays last time, what kind of relays are there available. And mostly here we are touch basing on the compressors relays. We say most compressors for ACs are hermetic, meaning they are sealed, and you'll see the relays from the outside. So this is a solid state relay, which means there are no moving parts. The other relays we have are current relay and potential relays, which have mechanical part, meaning there's an armature and there's a solenoid that opens and closes. So for this, there's nothing solid in it. It's completely, it has a clip on the outside, it has some chemicals, it does change resistance as current goes through it, and eventually the resistance will increase until it will cut off the start-up winding. Another solid state relay with a capacitor in it. So the capacitor also does come with the relay, it's attached to it, but the relay part is over here. And it does the same thing once the amperage drop has increased inside, the resistance of the relay will change and it will cut off the start winding. This is where we would see it. It's inside the compressor. If you see it's on the legs of the compressor, it's completely sealed and the whole assembly is from the outside. Operation. Can you see that from there? Yeah. Okay. So they are placed in series with the start winding. So if we want to look at it, if I were to draw the schematic for the winding. It is in series, so if this thing is closed, we'll have current going through it. If not, it will not operate. So that's being connected in series. If it was connected in parallel, it will look like that. Which is not the case. So this is useless in our layout here. So it's placed in series with start winding for a fractional horsepower hermetic compressor. What is fractional? What do we mean when we say fractional? Fractional horsepower. Anything less than 1 is a fraction of a horsepower. Could be a quarter, could be a half, could be a third. So when they say fraction is less than 1 horsepower. It has very low resistance. That's the potential, the solid state relay. As the compressor starts, the current flows with the start winding. So we have a current flow going through. The resistance to solid states windings start to rapidly increase with current going through it, and as the resistance increases, the current will be opposed by this resistance and you will not be able to go through. It's temperature based, so 3 minutes for it to come back to its original state. So you turn it off, there's a timer of 3 minutes that will not engage the compressor, and the whole thing will go back in 3 minutes. Again, it's, do you guys know what a thermistor is? A thermistor is something similar to thermocouple or thermostat, which it is usually used in a fridge or a freezer. And it does sense temperature based on, it senses temperature based on the change of the resistance. So as it cools off, the resistance will decrease, and as it heats up, the resistance will increase. So it is one mean to control temperature. Another solid state resistance, and you can see it goes from both sides, and here's an actuator. This is what it looks from the inside. If this is our running winding, we'll have the solid state resistance with the starter winding. And this is how the resistance increases as we increase the temperature. So usually when we increase the temperature, what happened to most metals, most material? Expands. So as we expand that, the resistance here is getting longer and more, and that's how it controls the running capacity. You don't have to know much about the intricacies inside, but usually there is resistance labeled on the side of the capacitor that tells you that what you're supposed to be getting if you test this resistance. It's very simple. Again, we just test for continuity and we test for resistance. Visible signs, if it's sharp, if there's any sign of burn, any sign of bulging, any sign of crack, or discoloration, that's an indication of that it went bad. So you can change that and change the function. It could be checked with an ohmmeter. For solid state, there's no usually a lot of relays, but you can check the resistance. If you have very high resistance, that indicates bad relay, and we're talking about the coil in here that changes with temperature. The last part we want to talk about in motors is bearings. And bearings are very important because sometimes, even though they're not very dire, it's very important to have an indication.
Sleeve bearings are cheaper, right?
Yeah. I don't know about the price, but they're more convenient, sleeve bearings. And last class I mentioned why don't we use ball bearing in compressors?
Because it causes a spark.
Yes, there's a possibility of a spark, possibility of friction, and possibility of one of those balls to leave the harness and cause a problem in terms of the spark or get stuck in the motor. So any rotating equipment requires some kind of bearing to hold the shaft or whatever is rotating and to counteract friction. Let me see. There are two types, ball bearings and sleeve bearings. Ball bearings, they have a harness or housing. Inside. And sometimes this is filled with oil. Sometimes there's nothing in it, or grease. And it's also, there's a sealant here. Sleeve bearing is basically two metals inside of each other. This is the shaft. Soft metal. What's an example of soft metal? Aluminum is soft. Yeah. What else?
Gold.
Huh? Gold is soft. Yeah. What else? Copper is soft. So you always see small soft copper layer in there. And again, you also want to have on top of this friction is a small layer of oil. Not a lot, just a little bit of oil. Oil have specific viscosity, means the resistance to friction, and it doesn't stick to the middle. So a lot of those motors require a few drops of oil just to spread between those two layers. And once the shaft starts to rotate, it will lift it off and depends on centrifugal force and stay in the middle. So that's called the sleeve bearing. Sleeve bearings are very common in small motors, but once the motor gets really big, you will need some ball bearing to take some of that weight. It will be more difficult to move a big shaft only with sleeve bearing. The friction will be very tough, and that's why I said when we leave a pump or a big motor for a while sitting there, it will be hard to move. So a ball bearing is designed with an inner and outer ring, enclosed by balls by use of separator. There's a small ring with holes in it to keep the balls in place because you don't want to be cramped or jammed together. Lubrication, permanently lubricated. They are done in a factory, they are press fit. That's why you don't see the balls that are inside. And the seal should be tight enough that the oil does not leak. And this is what happens usually, and especially in cars, you go too far, especially in hot days, and the seal a little bit melt or get dislocated, and the oil will leak. That's the first step. Then you get the grind, and the grind will get louder and louder and louder, and eventually, if you don't replace the bearing, it will shred, and the wheel will seize. Back lubrication, different type, or grease fitting. The grease fitting is you have to always lubricate every few years, and that was in old cars, again 70s and 80s. Every once in a while you go to a shop and they will pump some grease into the joints of the car to keep it in there. Okay, these you can pack and unpack and put some oil. Ball bearings again, so it looks like you take out the sealant, and this is the cover for that. This here is a sleeve bearing, has some bushing and some soft metal from the outside. Brass, bronze cylinders. Brass is copper mixed with nickel. Both are soft metals. If you have higher friction, higher weight. So friction is a function of weight and roughness. So the more weight you put on the surface, the more friction you will have. Also a function of the velocity. I'm not going to go too much into it, but again, how soft the surface is and how much weight you exert on it. For sleeve bearing, there's something called oil wick lubrication. In this case, you will have your bearing, and there's an oil reservoir which goes through a small, long wick and keep lubricating. Have you ever had an oil lamp? Forget about oil lamp. What about a candle? How does the wax get burned continuously and nothing, even though it is solid? How does it go through the wick to the tip and burn and keep pulling itself?
Turns to liquid and soaks up.
Yeah, how does it suck up?
Heat.
Heat and what else? Osmosis? Have you ever heard of osmosis? Okay, if you put a piece of tissue, a tip of a piece of tissue in water, what happens to the piece of tissue? The entire tissue. Yeah, slowly you'll see it, osmosis. It's how oil or water or liquid transfer through fiber slowly by exchange. Every molecule of the fiber will pull and pull and pull, and eventually that piece of fabric or tissue will be completely wet until it's completely dry. Plants do that, yeah.
The same concept was the lava lamp.
Lava lamp is different. Lava lamp is convection, free convection. In the bottom, the heat the wax. The wax, when it gets hot, it expands, it gets lighter, so it goes to the top. Because of buoyancy. As it goes to the top, it loses its heat, becomes heavier, and it sinks. So lava lamp is completely an explanation of free convection.
Inside of it's not water, right?
It's I think it's some kind of oil.
Some oil, right?
Yeah.
Because I see
But-
though that it never burns. They
Yeah.
keep saying.
It's basically of density, and it's also calibrated for the temperature you put in there. Somebody is putting those two substances that do not mix, and with the oil inside, so they can keep going back and forth. And again, that's a really good example of free convection, where you just see things go up and down. It's what you do in your room, but you don't see it. With the radiator, that's what you do. It's kind of like a lava lamp, up and down, up and down. Not in bubbles, of course, going to be in streams, continuously. So oil wick lubrication is the same thing. Yarn packed. That's basically, we put a lot of yarn and we fill with oil and wait for the oil to finish. It's not going to finish. Usually it takes a whole season to finish the oil, depending on the temperature and the right type of oil. And there's also oil ring lubrication. Hopefully I have a picture of that. So this is an oil wick. It's where you fill the oil and it will touch the base of the shaft and it keep it lubricated as it moves. Yarn packed. So the difference here is the oil goes only from one side and goes through, spread itself over the shaft. Over here, we have a complete ring full of oil on all sides. In this case here, we keep an oil tank at the bottom, and as the shaft and bearing circulate, it will dip itself in the oil and goes up. So in your engine, do you think your engine is filled with oil? No, only the bottom side. That's why you do not overfill your oil reservoir with oil. Till you 5 quarts, stick with 5 quarts. Why? Because what happens in your car, the crankshaft, as it spins, it will spray oil over the place. And that will lubricate the engine. If you put too much, the amount of spray you will have is very inadequate. If you have very, very low oil, there will be no spray. And that's why when the oil gets old and heavy, it will not spray very well. So the engine is actually spraying oil over the place while it's running. If you overfill the engine with oil, what will happen? You have reduced its movement and made it hard to spin. That kind of concludes the part about bearings. So we talked about relays, we talked about windings, and we talked about bearing. The last part we want to talk about is a motor drive. We have 2 drives. I'm not going to make it very complicated. Either direct drive or a belt drive. You done with this? So what do I mean when I have direct drive and belt drive? Actually, I have a picture here. Picture is good. So this is direct drive, which means whenever I have spinning, goes with the same RPM as the motor. So they are connected with something called a coupling. So the RPM of the motor equals the RPM of the pump. That's their drive. And sometimes we have different kind of couplings. Some of them are rigid and some of them are flexible. Again, going back to the car example. You have a compressor in your car, right?
Yes.
The compressor runs by the motor. The engine runs the compressor. And also the engine runs the alternator. Is the RPM for the engine constant or variable?
Variable.
Variable. You hit the gas all the time, it goes up and down, up and down. How do you think the alternator or the compressor adjusts itself? Otherwise they see it going back and forth, right? And the alternator will go up and down. But they don't. What do they put in there?
Pulley?
Huh?
Pulley?
It's not always about the pulley, because also the pulley is going to change the speed. There's a clutch. There's a clutch that actually triggered by the speed, so it will maintain itself at certain speed, which is around like 1,000 RPM. So if you go up even to 5,000, it will disengage. Once you overspeed, it will disengage and maintain itself at that speed. So pay attention to that. I mean, it's kind of interesting, and that's what they have here for this kind of coupling, where you'll see one armature or one piece of the shaft going faster than the other. It slows down. They have a clutch in it that will slow it down. So the main point here is like notice what kind of coupling do you have and stick with the right coupling. Some of them are also adjustable. And that's why when your car RPM is lower than 1,000 RPM, the car will kind of stall, because everything is triggered to run at 1,000 RPM. The V-belt drum is the second thing, which we have the motor outside, and it's very convenient to run one or more pulleys at the same time, and it's called the V-belt. It's called the V-belt. It's called the V-belt because it looks like a V. That's the housing, and this is the belt. And there is a specific ratio between the pulley and the motor speed. This is a simple small equation to know what is the ratio between the diameter of the equipment and the diameter of the motor. So as you see, there's a ratio between them, and it goes back to the RPM of the motor and the RPM of the equipment. You might need that if you have to change the motor RPM, because that will change the fan RPM or whatever you put in the other side. For the belt tension, usually is manufacturer specified, and there's a tool called belt tensioner where you turn off the equipment and you press against the belt and you see what is the tension in the belt. If the belt gets too loose, what happens? Slips, and you lose some RPM. If it gets too tight, that's how you break your bearing, and you will tilt the shaft a little bit, and over time it will break. So you want the right tension. So far, this is what we covered. Back electromotive forces, that's what happens when the motor spins. Ball bearing, over here. Bearing in general is whatever carries the shaft. Current or magnetic relay, they drop the startup winding based on the back electromotive forces. Direct drive, coupling, full load amperage. What is full load amperage? That's the stabilized amperage that the motor draws once it's on. Locked rotor amperage. That happens when we start the motor from zero and the motor is not moving. If you seize the motor, if you stop the rotation, this is what you're going to get, the locked rotor amperage. Potential relay, sleeve bearing, that's sleeve bearing. Starting relay, could be magnetic, could be current, it could be solid state, V-built. Yeah, that's it. I have a nice video about shaded poles.
Yeah, it's turning clockwise. Those motors use magnetism and field to determine which way they run. There are no contacts or brushes running on the armature. In order to reverse the rotation on this motor, we need to reverse this field. This motor is designed to run on AC. AC voltage is reversing itself 50, 60 times a second, depending on where you're at. And as long as the motor is made to where you can flip this field over, you should be able to reverse the rotation. Pull these apart, sometimes there's a bunch of little spacers or washers in here. Just want to make sure that you put everything back together the way it was. This field was on here this way. We're gonna turn it over. Put it back together.
This is a shaded pole motor.
Let's give me a hard time. You can see that this has slipped a little bit. I'm gonna tap that with a hammer, line those back up again. I just adjust my vise to support the main part of this field.
This is the
I'm
shaded
gonna
pole.
take a pin punch and just tap on both sides of these until I get this to slide even with the other part. Now both of those are flush, ready to go back together. So a little friendly persuasion with a hammer. Let's line back up again. Put this on here. It's that easy. As long as this is made so that you can flip over the field. You can reverse the rotation on most of these motors. These cores are made on a bunch of stacked plates. They're riveted to hold them together. And then that core is made in two pieces so that you can make this separately. Slide it on this piece and then press it together. These can only go together one way because there's an alignment or an indexing notch over here. This transformer core generates magnetism. That magnetism changes with every cycle of the line frequency. Generates a lot of heat. These windings here get very hot. I have another video that shows you how to make a small fan put on here to keep this cool. A lot of these induction motors and shaded pole motors are being sold without fans. It seems to be very difficult to find the fans to go with the motors, so you have to make your own. And making your own is not that hard. This motor is relatively low torque as far as the armature is concerned. This is turning about 3,500 RPM, goes into a gearbox. The gearbox is 183 to 1 reduction, so the output shaft is turning 19 RPM, and there's a lot of power here. One of the strongest induction motors that I have found.
Okay, that's an induction motor. 7 minutes. Okay, I'll keep this video for Monday. Basically, the guy takes apart the whole handrail and put it back together and show you how it works outside. It's very fascinating to see how we can use the pressures and so on. You guys doing the presentation?